map a file with the map shared flag, you're telling the OS you want changes to be visible to all other processes mapping that same file. The kernel ensures this by having the page tables of all participating processes point to the same physical pages in RAM. A write from process A to a mapped memory page is instantly visible to process B because they are literally looking at the same piece of physical memory. The kernel's page cache acts as the single source of truth. Now, what about map private? This creates a copy on write mapping. Multiple processes can start by sharing the same physical pages for reading. But the moment one process tries to write to a page, the kernel transparently duplicates that page, gives the writing process its own private copy, and updates its page table. From that point on, its changes are isolated. This distinction is critical for designing robust systems. Are you building a high-performance IPC mechanism where processes need shared state? Use map shared. Are you loading a shared library where each process needs its own pristine, unchangeable view? Map private is your answer.
We've seen how data gets into memory, but how does it get back to the disk? When your application writes to a memory-mapped region, it's just modifying a page in RAM. The CPU flags this page with a dirty bit in the page table entry. This is a signal to the kernel. This page's content in memory is newer than what's on disk. The write to disk doesn't happen immediately. That would defeat the entire performance benefit of mmap. Instead, the kernel uses background processes, often called writeback daemons or flusher threads, to handle this asynchronously. These kernel threads periodically scan for dirty pages. They gather them up and write them back to the underlying storage device in an optimized, sequential manner. This asynchronous writeback is a fundamental trade-off. It provides incredible write performance because your application isn't blocked waiting for slow disk I/O. However, it also means there's a window of time where modified data exists only in RAM. If the system crashes before the writeback occurs, that data is lost. For applications like databases that require durability, this is why they use mechanisms like msync to explicitly force the kernel to write specific dirty pages to disk, guaranteeing that a transaction is safely persisted.
So let's bring this all together. Why does understanding mmap coherence and writeback matter to you? For junior developers, when you use a tool like SQLite or an embedded database, you're likely using mmap under the hood.